Alrighty, let's start this lesson with some error analysis. The following expressions have errors. What's wrong with each answer? Alright, first thing I see is this expression, x to the fourth times x to the third. I know when the bases are the same and I'm multiplying, if there was a coefficient, I would multiply the coefficient. But here there's just technically a 1 and a 1, which would leave me with a 1. Then I keep my variable the same, x, and when you are multiplying variables, you add the exponents. 4 plus 3 is 7. But the answer, they got 12. Let's think, how can we get 4 and 3 to equal 12? Oh, they multiplied. So what's wrong? They should have added exponents. I'll just abbreviate exponents. All right, so let's look at the next one. When you're doing product rule again, when you're multiplying, you multiply the coefficients. 4 times 5 is 20. You keep the variable, so we keep w as w, and we add the exponents. 5 plus 7 is 12. Well, I see they did get the w 12, but they got 9. And how did they get 9? They did 4 plus 5. They were supposed to multiply the coefficients. They should have multiplied the coefficients. Perfect. All right, let's look at the next one. The next one is an example of a power to a power rule, when you have exponents inside and you have exponents outside of the parentheses. And let's see what they did wrong. Well, they kept the g, that's good. But this 2 and 5, when you have an exponent inside and outside, think of it like distributing. You should be doing 2 times 5, which equals 10. But they only added, which is not correct. They should have multiplied the exponents. Alrighty, let's look at the next one. So, everything inside the parentheses gets an exponent. The 2 has an exponent of 1, it's invisible, and the m has an exponent of 3. And we're supposed to multiply those inside exponents by the outside exponent of 4. So it should be 2 to the fourth, and m 3 times 4 is 12. They did get the m to the 12, but they forgot about the exponent of the 2. They forgot to do 2 to the first raised to the fourth, which is 2 to the fourth. And then just for your acknowledgement, remember that 2 to the fourth does not mean 2 times 4. Instead, it means 2 times 2 times 2 times 2. Good. All right, let's look at the next one. We keep the coefficients the same. 1 times 1 is 1. That's good. Then we keep the we don't keep the coefficients the same. We multiply the coefficients. 1 times 1 does equal 1. Then we keep the variable the same, and then we add the exponents. Negative 2 plus 5 does equal 3. So they actually did this one correct. Perfect. And if you wanted to double make sure this is correct, let's make a number for y. Let's make y 2. So we can make it 2 to the negative second power, and then multiply it by 2 to the fifth power. And let's see, is that same as doing 2 to the third power? Yes, they get the same answer, so they are correct. All right, and this last one, 2k to the 0 power. All right. Anything to the 0 power does equal 1. So this part right here equals 1. But we still have this 2 on the outside, and 2 times 1 equals 2. So they forgot about the outside 2. They just seen exponent of 0, and they just figured the whole thing was 0. But that 2 doesn't have an exponent of 0. That 2 has an exponent of 1. Alrighty. Now, today we are going to learn how to simplify linear expressions and find equivalent expressions using exponent laws. So let's look at today's lesson. A key part of any work in algebra is manipulating expressions to produce equivalent expressions, ones which have equivalent or equal values. One part of writing equivalent exponent equivalent exponential expressions is remembering the properties of expressions. So let's just look at the exponent rules. The zero exponent rule. That says anytime you have a number or a variable raised to the 0 power, it's going to equal 1. Then the product rule. The product rule says you multiply the coefficients, the outside numbers, you keep the variables, and you add the exponents. Quotient rule. Quotient rule happens when you're dividing. This one, again, would say that you divide the coefficients, you keep the variables, and then you subtract the exponents. Now, power of a product or power of a power rule says that each thing on the inside gets an exponent, so the 1 and the 1 if you don't see one, and you multiply it by the outside exponent, kind of like you're distributing that exponent. If you had a power of a quotient rule, that would just say that you're giving each thing in a fraction the exponent that's on the outside. Power of a power rule, we multiply that on the outside. And the negative exponent law says if you have a negative exponent, you could bring that value to the bottom of a fraction and make the exponent positive. There will be a video posted on reviewing exponent laws if you need to see that. Alrighty, so let's look at this guided example. Consider the expression 3x plus 2 times 3x minus 1. We want to evaluate this expression when x equals 2. So, we could either just tell our calculator x equals 2, or we could do this by hand. So 3, then x becomes 2, so 2 plus 2 times 3, replace the x with 2, minus 1. Let's type this in. 3 raised to the 2 plus 2 power times 3 raised to the 2 minus 1 power, and that gets us 243. Okay. Now the next thing says, use the product rule, which says that you keep the base and you add the exponents to simplify the expression. So I'm going to keep the base of 3, and I'm going to add x plus 2 plus x minus 1. So that would give me x plus x is 2x. 2 minus 1, or 2 plus negative 1 is 1. And now evaluate this new expression when x equals 2. So 2 raised to the 2 plus 1 power. Let's do this. 3 raised to the 2 times 2 plus 1 power. Hey, that equals 243. So what do I notice? If you use exponent laws correctly, the value will stay the same. Right now, I figured out that this is true for the product rule. So right now, I'm just wondering, is this true for all the exponent laws? Let's look at this next example. Practice writing each of these in simplest form by using the product rule. All right, keep the base, and then 6 plus x is just going to be 6 plus x. Or I could write it as 5x plus 6. Either of these are correct. All right, this next one, I'm going to keep my base of 2 the same, and then I'm going to be adding x plus 7 plus 4x minus 3. So x plus 4x is 5x, and 7 plus negative 3, or 7 minus 3, is 4. Good. This 10 has an imaginary 1, so 10, 2 plus 5 plus 1, because I'm adding the two exponents, would give me 2t plus 6. And this last one, I keep my base of 4, and I'm adding the exponent negative x plus 6, and I'm adding it to the 7x minus 3. So that would be 4. Negative x plus 7x is 6x. 6 plus negative 3 is positive 3. So these are all equivalent expressions that if for the original statement you typed in that x or whatever the variable is equaled any number, as long as you use that same value for the variable in the final expression that you wrote, they would stay equal to each other. For example, let's look at D. If I did 4 and I made my x's 3, let's just say. So I put negative 3 plus 6 times 4 raised to the 7. I'm making my x 3 minus 3. I would get that value. That's a huge value. All right, and now let's do that for the new one we made, 6. Make the x 3 plus 3. Look, it's the same exact number. Alrighty. So let's look at this challenge. Explain why the expression 9 times 3x must be equivalent to the expression 3x plus 2. All right, 9 times 3x. Well, I know the only way I could use the product rule when I'm multiplying is if the bases are the same. Here I have a base of 3. So I have to think using only things I know about exponents. How can I turn this 9 into a 3 as well? If you remember anything about perfect squares, and back to like the first unit we did, I could turn 9 into 3 raised to the second power. Because 3 to the second power is equivalent to 9, and this would help me because now these bases are the same, so I would have 3 and 2 plus x. Product rule says I add those, x plus 2. And so 9 times 3x is equal to 3x plus 2 because 9 equals 3 squared, and 3 squared times 3x is 3x plus 2. Good job. And you could also see these are equal because let's say we make x 2. I always like to make x 2. That would be the original one. And this new one, x is 2 plus 2. They equal the same value. All right. Let's look at this when we have the power of a power rule. All right, let's see. Evaluate this expression when x equals 2. All right, let's do the original one. 3. X is going to become 2 plus 4. And then the outside I'll have 6, making the x a 2. All right, let's type this in. 3 raised to the 2 plus 4 raised to the 6 times 2. All right, that gives me a huge number. Equals 2.2 times 10 to the 34 power. All right. Use the power of power rule to find the equivalent expression. So I have to multiply. You have to multiply what's on the outside by everything on the inside. So it would be 3x times the 6x plus 4 times the 6x. So that would leave me with 6x squared plus 4 times 6 is 24x. And let's see if this is true when we have that x equals 2, what value we get. We get 3 raised to the 6, 2 squared plus 24 times 2. Hey, we get that big same old number. So what do I notice? The expression stayed equal when using power to a power rule correctly. Perfect. Alrighty. Let's look at this practice. Write each of the following in simplest form by using the power of a power rule, which just says that we have to multiply the outside exponents by the inside. So those would be 2. 4 times 7 is 28. Let's look at the next one. X. 9 times 2 is 18. The next one, 4. 5 times x is 5x. And 7 times 5 is 35. And lastly, 3. 4x times 3 is 12x. And 1 times 3 is 3. Good. Alrighty. And let's look at this challenge problem. Which of the following would be equivalent to 8x? Okay, let's look at all these. 2x plus 3. Which one is equivalent to x? 8x. Well, here, 2 to the third is equal to 8. 4 to the second, that would be 16x. So I don't think it's this one. And then I don't think it would be 1 or 4. Let me try my trick that I know. Let's make x 2. So 8 squared would be 64. So let's try each of these. 2. I'm going to make my x 2 plus, and then let's see what this gets us. I'm just changing my x's to 2 because I want to see which one also gets me 64. So my answer can't be 1. Let's see if my answer could be 2. 2, 3, and I'm going to change my x to a 2. 2 raised to 3 times 2 power. Hey, that equals 64, so I'm thinking that could be the answer. Let me just retry the other, number 3. That equals 256, so no, that is not my answer. Now let's look at the last one. 4 raised to the 2 plus 2. That's not my answer either. So my answer indeed is 2. So we want to make sure that we're able to use exponent laws to rewrite exponential expressions in both directions. And let's look at this challenge question. Which expression below is not equivalent to 25 3x plus 6? These answer choices look crazy, so we will use our calculator to solve more complicated problems like this. The following technique is possible anytime we see a multiple choice question that uses the word equivalent. So, you can make x any number you want to make it. I'm just always going to make x 2. 2 is a nice simple number, but you don't want to use 1 because we know how sometimes when you all the time, when you multiply 1 by a number, the number just stays the same. So we don't want to do that. All right. So now I'm going to type in each of these answer choices and see when I make x 2, which one gets me that crazy looking number. Oh, look, it's the first one. Let me just type in the other ones just to show you that they don't work. 25 raised to the x is 2 plus 2 raised to the third power. Oh, remember, I'm looking for something that's not equivalent. So this and this is equivalent. Look, if I didn't check the next one and realize that they were both equal, I would have chose the wrong answer choice. So I'm looking for which one doesn't get me that answer. That one also gets me the same answer. So I'm assuming the last one's not going to get us the answer. Let's see. Yep, there we go. That one is not equivalent. All right, and now we are going to move on to all type of Regents problems where we are going to use this technique. So let's look at the first one. It says, Miriam and Jessica are growing bacteria in a laboratory. Miriam uses the growth function. Miriam uses f of t equals n2 to the t power. Then Jessica uses the function g of t equals n4 to the t power, where n is the initial number of bacteria and t is the time in hours. If Miriam starts with bacteria of 16, how many bacteria should Jessica start with to achieve the same results? So she's having 16 here. Her number of bacteria is 16. And what is 16 squared in the calculator? 16 squared in the calculator would get us 256 raised to the t power. All right, and we want to know somehow how can we get this n to the fourth to also be, because we want them to be equal, so we need this n to the fourth to equal 256. So let's try the answer choices. The first answer choice would be 32 raised to the fourth power. Ooh, that's going to be too big of a number. Let's try 16 to the fourth power. Too big of a number. Let's try 8 to the fourth power. Still too big. And 4 to the fourth power. Ooh, that works out nice because 4 to the fourth power is 256t. So our answer would be choice 4. Another way we can do this is we can make t equal 2. We're just going to, for all these problems, we're going to make t equal 2. So for the first one, if we have 16 raised to the 2 power and we're making t2, we would end up with that number. And now let's try each of the answer choices. If I try 32 raised to the 4th power times I'm making t2, that would not be the same number. Let's try 16 to the 4th power where t is 2, not the same number. 8 to the 4th power where t is 2, no good. And what about 4 to the 4th power where t is 2? that does equal the initial number we got. So it would be answer choice 1. 4, I meant, sorry. All right, let's look at number 2. Number 2 is saying the growth of a certain organism can be modeled by this, where C of t is the total number of cells after t hours. Which function is approximately equivalent to C of t? Well, let's first see, what is this number raised to the 24th power? Let's see that. What is 1.029 raised to the 24th power? It equals 1.95, which could be rounded up to 1.96. So we can get rid of 1 and we can get rid of 2, because I like this number inside the parentheses. When I do 1.09 raised to the 24th power, I can just replace that with 1.986. My exponent is still going to have the t there. I'm not going to divide the t by 24, so my answer would be choice 3. Now, let's say that makes no sense to you. Another way we can do that is we can use the original problem, take the original problem, and we can make t equal to 2. So let's see, when I make t equal to 2 here, what number would we get? 1.029 raised to the 24th power times 2. I would get, I'll just say 39.44. Now, let's try each of these answer choices by making t 2. So let's try the first one. 240 parentheses 0.083 raised to the 24 times t is the 2 power. That would equal 3.13 e negative 15. Not going to be the answer. Let's try the next one. 10 parentheses 0.083. And we're going to raise it to the t power, which we're making t2. That would be 0.06889. Not going to be the answer. Let's try the third one. 10, 1.986 raised to the t power, which t is 2. And guess what? That equals the 39.44. So 2 would definitely be our answer. Now let's look at number 3. Number 3 is saying a computer application generates a sequence of musical notes using this function, 6 times 16 to the n power, where n is the number of notes in the sequence. All right. So we can make n equal to 2. I'm just going to always make n equal to 2. When I get that, I get 6 parentheses 16 to the second power. I get 1,536. All right, now let's look at each of the answer choices. I'm just going to replace each of the n's in the answer choices with 2 and hope that one of them gives me the same 1,536. So answer choice 1, we would have 12 parentheses 2 raised to the 4th power times n, which is 2. And that would equal $3,072, which is not the same answer that we got originally. Now let's look at 2. We're going to have 6 times 2 raised to the 4th power, and we're making n 2, which would be 1,536, which is our answer because that's the same as what we got originally. And let's just understand how they got this. Well, what is 2 to the 4th power? 2 to the 4th power equals 16, the original number. All right, let's look at number 4. Number 4 is saying Mario's car depreciates in value at a rate of 19% per year. The value v after t years can be modeled by this function. Which function is equivalent to the original? All right, so let's again make t equal to 2. I just like the number 2. 0 could sometimes be a little iffy. 1 doesn't really get you that good of results. Make t equal to 2. So let's type in the problem. 15,000. Then we're going to have 0.81. And instead of t, I'm going to raise it to the 2nd power. And that gives me 9,841.5. And now I'm trying to see which one, when I make T2, would I also get 9,841. So let's look at answer choice 1. Answer choice 1 is 15,000, 0.9 raised to 9th power times T, which T is 2. That would equal 2,251. Not going to be my answer choice. All right, let's look at answer choice 2. 15,000, 0.9 raised to the 2nd power times t, t is 2. Oh, guess what? That equals 981 9,841, which is what we needed. And why does this make sense? Well, the only thing that I see different here is they have the 0.9 raised to the second power. And what is 0.9 raised to the second power? That equals 0.81, which we originally had in our original function. All right, let's look at question 5. Nora inherited a savings account that was started by her grandmother 25 years ago. This scenario is modeled by this function, where A of t represents the value on the account in dollars t years after the inheritance. Which function below is equivalent to A of t? Again, let's just make t equal to 2. It doesn't actually matter what number you make t equal to, but I'm just going to make it equal to 2. So let's try this. 5,000, then parentheses 1.013 raised to the t power, which t is 2, plus 25. So I need to get something that is 7,086. All right, let's look at answer choice 1. 5,000, parentheses 1.013 raised to t power, which is 2, raised to 25th power. And that gives me 9,537. I don't like that, so not going to be the answer choice. Let's look at number 2. 5,000, parentheses 1.013 raised to the t power, which is 2, plus parentheses 1.013 raised to the 25th power. And that gives me 12,000, which is not going to be my answer choice. Let's look at number 3. We have 5,000 raised to the t power, which t is 2, then parentheses 1.013 raised to the 25th power. That's not going to be my answer choice. And number 4, 5,000 parentheses 1.013 raised to the t power, which is 2, parentheses 1.013 raised to the 25th power, which that is our answer choice. And let's understand why. Here they're saying t plus 25. You only add exponents together when you're multiplying. Here you're multiplying this number with this number. They're both the same number, so that's why it stays 1.013. And you add the exponents, t plus 25, which is what's happening in the original function. Number 6. The number of bacteria grown in a lab can be modeled by this function, where t is the number of hours, which is equivalent. Again, I'll make t equal to 2, and what do we get? 300 times 2 raised to the 4th power times t, which is 2. And that gives us an answer of 76,800. And let's see, when I make t equal to 2 for the answer choices, which one gives me the same answer? 3,000 times 8 raised to t power, which is 2. That's 19,200. Not going to be my answer choice. Let's look at number 2. 3,000 times 16 raised to t power. T is going to be 2. And guess what? That gives us the same 76,800. So our answer would be choice 2. And why does that make sense? Well, what is 2 to the 4th power? 2 to the 4th power is 16, and that's the only one that has 16 in our answer choice. Now let's look at number 7. Number 7 says the population of a city can be modeled by this, where P of t is the population after t years. Which function is approximately equivalent to P of t? All right. Let's see. What is this raised to the 7th power? 1.0005 raised to the 7th power would be 1.0035, which would be either answer choice 1 or 2 or 4. And what's the difference between 2 and 4? Well, 4 they changed the other number. There's no way I'm changing the other number, so my answer would be choice 2. But let's use our method to see why this makes sense. We're going to make t equal to 2, and let's see what we get. 3,810, parentheses 1.0005, raised to the 7 times t, which is going to be 2, and that equals 3,836. If you try the first answer choice in, you would get 3,810, parentheses 0.1427, and you're going to make t equal to 2. Not the same. Let's try number 2, 3,810, parentheses 1.0035, And let's make the exponent 2. Hey, that is the same, so it's answer choice 2. Let's look at number 8. In an orgasm, the number of cells CD after D days can be represented by this function. This function can also be expressed as, well, we're going to have to keep the 120 the same, so it's not going to be 1 or 2. And now what is 2 to the third power? 2 to the third power is 8, so it's number 4. But let's see if we make D equal to 2. If you put 120 times 2, raise it to 3, instead of D, you're going to put 2. You would get 7,680. And if you try all the answer choices, let's just see the last one. Make it times 8. Instead of D, we're going to put 2, and that would be equivalent. So that's why it's answer D. Let's look at number 9. A laboratory technician used the function this to model her research. Consider the following expressions. I'm automatically going to make m equal to 2 because I can't be bothered. So 2 parentheses 3, raise it to the 2. Instead of m, we're going to put 2 plus 1. I need to get an answer of 486. Now let's try each of these. For I, 6 times 3, raise to the 2 and make m 2. That would be 486, so this is definitely true. I need to have 1. So it needs to have 1 in it, so it's either going to be answer choice, it needs to have I in it, so it needs to be either answer choice 1 or 3. Now let's look at number 2, double I, 2. So 6 parentheses 6, raise it to the 2 and make m2. Would not be the same number, so it's not going to be anything that has 2 in it, so definitely have to get rid of answer choice 4 and 2. And now let's look, is it going to be 3? 6 parentheses 9, raised to the 2 power, this is equivalent to, so it's 1 and 3, which is answer choice 3. And let's look at the last exponential equivalency expression that we have. Materials A and B decay over time. The function for the amount of material A is that, and the amount of material B is this, where T represents times and days. On which day will the amounts of materials be equal? Well, initial day would be when T equals 0. So let's plug in T equals 0 for both of them. This is for A, and this is for B, the answer that I get out of it. So I would do 1,000, parentheses, 0.5, raise it to 2, and I'm making my T be 0, so I would get 1,000 when I do that. And let's see what I get for B. B is 1,000, in parentheses I put 0.25, and I raise it to the 0 power, that would be 1,000. So far, the initial day could work. So that means every day right now could maybe be the case. Let's look at number 2. Alright, if I plug in 2 for A, 1,000, parentheses 0.5, raise it to the 2 times, now we're talking about second day, so that would be 62.5. And let's look at B. 1,000 times 0.25, and we raise it to the second power. Oh, look, that's 662.5. So it could also be day 2. Let's see if it could be day 5. 1,000, parentheses 0.5, raise it to the 2 times 5 would be 0.97, and let's try B. 1,000, parentheses 0.25, and let's raise it to the 5th power, and that would also be the same thing, which means this one works. So I could just assume that every day works, because I can't just choose one of those 3 if all of them are working, so every day is good. And that wraps up our lesson on answering Regents questions with equivalent expressions using exponent laws. Nice job.